this. All right. Let me practice. Nope. Yeah, maybe it has to be on.
Yeah.
That helps. You don't want to appear in the video, you know.
Oh, here you go.
Okay, it works.
Yeah, just go down there.
To advance, you have to go down.
Yeah.
Okay, all right, okay, all right. Okay. All right, so what we will try today to finish, I'm going to review a little bit important sampling. There is a lot of details that I left out. You know, we went very fast when it comes to convergence, but since we're going to cover sequential Monte Carlo methods later on, in early November, I'm going to come back to those slides because they are important research-wise. So what I'm going to do is give, the main topic is going to be Gibbs sampling, but I am going to try to review a little bit important sampling and give you some weird application just to motivate you that with statistics you can do anything you want to. All right. So as a reminder, I will assume this is the light. Nope. Oh, maybe this one. Yes. All right. So I remind you basically, if we have to compute things like the expectation of some function h of x with a distribution f, and f is a difficult distribution to sample from, what we do is we introduce this importance distribution q, and rather than sampling from f, we sample from q, and effectively what we need to do is keep track of the weights. So we have to adjust basically what we integrate, where we take these averages is not of h, but h times f over q. And we discuss both the normalized and normalized versions of important sampling, so I'm not going to give you all the details. But at the end of the day, if you want to estimate this, with standard Monte Carlo, you get something that looks like that. Okay, so it's exactly as your vanilla Monte Carlo. The only difference is every sample comes with a weight f divided by q. Again, f is the target distribution. The notation may be slightly different from before, and q is this important sampling distribution. Okay, the only really guarantee that you need to satisfy here is that q basic, you remember when we did accept reject type of algorithms we said q has to be on the top of the target distribution, in this case f. So the same is true here. So since we sample from q, this needs to be satisfied, and more importantly, the distribution q has to be fatter tails than the target distribution f. Okay, and certainly in regions where the distribution is positive, q has to be positive. All right. There are many criteria for guaranteeing that important sampling is going to work, and effectively this is the first term from the variance of the function h. So this thing has to be finite. Okay. There are much more simpler forms. Basically, the most simpler form would be that the weights basically don't blow up, so that the weights, the absolute values are less than infinity, and that would be, actually, if that's the case, this will also be satisfied. Okay, so which means don't be choosing q that is anything without actually checking that the weights have finite variance. Certainly this can get you in trouble in high dimensions, and I think we did one example in the earlier lecture. All right. I want to do, we will revisit this when we do sequential Monte Carlo, but I wanted to do sort of a little perturbation of important sampling that goes with the name sampling importance resampling. So the algorithm is called SIR, and it is a very popular algorithm. So let me very briefly describe what we do to important sampling to simplify things. So you agree with me that if you do important sampling, you sample from a distribution Q, and then the approximation, the Monte Carlo approximation of P, is this delta function centered on each sample times the weights, right? I mean, this is what we came about in the previous lecture, okay? So if you calculate the expectation of any function, effectively you will get the values of the function at xs times the weights and then summation on s, all right? So that's the Monte Carlo approximation for important sampling, where the samples xs come from the distribution Q. All right, so think now that you do the following thing. Think of resampling from this distribution with probabilities that they are proportional to the weights Ws. So effectively think of resampling particles S, right, and I call them this XS particles S, okay, with probabilities that correspond to a discrete distribution with weights W1, W2, W capital S. You remember how to sample from a discrete distribution? We did this in the very first lecture. The idea here is I want to simplify this approximation. Why do I want to simplify? Because maybe I have some samples with huge weights and some other samples that are basically irrelevant. So why summing over something that has very little weight? So if I resample from this distribution proportionally to each of these weights, I will only resampling particles XS that have significant weight. The rest will not be sampled, will not be important. Okay? So when you do this, effectively, so here's the idea. So Ws have the normalized importance weight, and we're going to sample XS with probabilities that they are proportional to this weights Ws. And what I have here is a little proof that effectively the new distribution that is going to come from this process, it actually is equivalent to this original distribution. So let me go very fast through the derivation. Can you look at this? So this P hat is the distribution that is going to be derived from this if I resample with probabilities proportional to the weights Ws. So look at this equation first and tell me where, so this is like the CDF of this new distribution after resampling. Tell me from where this thing is coming from and if it is familiar. So I said I'm going to resample the way I resample from discrete distributions, all right? And the discrete distributions basically will be with probabilities Ws. So does this remind you anything? This equal to that? You remember this is the indicator function, right? So I'm looking for this new distribution that comes after resampling. This is like the CDF, is the probability that X is less than a given value. And here what I do is I put the indicator function times Ws. So from where is this coming? This is the CDF of what type of distribution? Does this remind you the CDF of any distribution we have seen? How do you compute the CDF of a discrete distribution? Do you compute it like this? No? I mean, you're summing basically all the weights, right, for the particles that are less or equal to x0. Because I said I'm going to resample proportionally to the weights. All right? So this is the CDF of the discrete distribution that comes from the weight that I resample. And then what I do is I substitute the weights as the ratio P over Q, where for P, this P currently is the anormalized distribution P, okay? You remember, you know, when you use the anormalized weights, then you also have to put the normalization factor here on the bottom. So this is the anormalized weights divided by this normalization factor, where you sum over all particles. And then just to make calculations easy, I make the summations integrals, and because x are coming from the distribution q of x, so this looks like that, these integrals, okay? And q cancel out, q and q cancel out, and this curly of p divided by this normalization factor, it gives you the distribution p of x, and this gives you nothing else but the CDF of the original distribution p. The idea here is, if you resample from this, right, you're actually getting an approximation of the exact CDF of the distribution of interest. Now, why do you want to resample from this? Because you will get rid of lots of the particles that have very small weights, and more importantly, the distribution will look like a standard Monte Carlo approximation where the weights would be 1 over the number of particles that you sample from. So the fact that you sample proportionally to the weights disappear from the picture, and the Monte Carlo approximation, you remember if you have n samples, you have 1 over n, so here we have 1 over s prime, where s prime is the number of samples in the resampling process, and this number of samples is significantly less than this s, because many of these particles that we had in this approximation will actually not appear there. We have very small weights, so you will never sample them. Bottom line is, right, when you look at papers, even though they do important sampling, you may wonder, where are the weights? Well, the weights have disappeared because maybe at every step of the process, when you have an approximation like this equation on the top, you resample, and then the approximation looks like what you see on the bottom. This is very standard type of calculation that you do with important sampling, okay? Especially if, as we will see, if it is a dynamic problem and you have to come up with approximations like this, let's say, in time. So in every time, what you would like to do is resample, get the approximation look like that, and then proceed to the next time step. We will see this. If you didn't get it clearly, we will see this again when we do sequential important sampling. All right, so let me do a weird application as I promised, and there are many things that somebody can do. We can spend many lectures on this. If I ask you, solving AX equal to B, how you're going to do it, maybe you forgot, all right? But AX equal to B is sort of the most fundamental problem in all sort of computations. Everything at the end of the day becomes AX equal to B. And the question is, can we actually solve AX equal to B using important sampling? There's nothing stochastic here. A is a matrix, B is a vector, X is a vector. We want to solve AX equal to B using important sampling. So that looks weird to start with. Is that possible? All right. So let me first do some tricks, and they work in most practical cases. So what I'm going to do is I'm going to multiply with the matrix G, all right? And then I'm going to set G times A equal to I minus B, and I'm going to design this matrix G in such a way that the spectral radius of B is less than 1. You remember what is the spectral radius of a matrix? It's the largest eigenvalue of the matrix, okay? You will see a reason why you want the largest eigenvalue to be less than 1, okay? Because effectively we're going to do sort of a Taylor series expansion. So look at this now. If GA equal I minus B, I call this H. So really my equation becomes I minus B times X equal to H. And you remember the Taylor series expansion, 1 divided by 1 minus X? Does it click? 1 divided by 1 minus X? Now, you remember? 1 divided by 1 minus X. What's the Taylor series expansion? One plus x squared plus x cubed, no? Come on, you have your computers, just say Taylor series expansion, 1 divided by 1 minus x. Okay? All right. So the Taylor series expansion is basically, so remember we have I minus B times X equal to H. So it's really the I minus B inverse times H, that's the solution X. And the inverse in the Taylor series expansion is nothing else but this summation on B to the power K times H. All right? So the solution of the linear system of equations is this infinite summation from K equal to 0 of B to the power K times H. Can you appreciate now the reason why I wanted the eigenvalues to be, the maximum eigenvalue to be less than 1? Because otherwise the B to the power K, right, when you take B to the power K in a spectral form is the eigenvalues to the power K, you want to be sure that that thing doesn't blow up. Okay? So, so the solution basically of a linear system of equations is written as X equal B to the power K times H, and you may say, yeah, who cares? Where is the important something? All right, so let's see. So I am going to write this, so here I have B to the power K. How do you multiply B K times? You multiply B times B times B times B, right? K times. Don't you do actually B times I1, B times in component form, I1, I2? How do you multiply matrices? B ik minus 1 ik in K steps, and then you sum over all these indices. How do you multiply matrices? Right? This way? Okay. So the solution, and you notice here, by the way, I write one of the components of the vector x. And that's actually an amazing result you will see shortly, because in all existing methods for solving ax equal b, you compute all of the x together. Here, I am writing one equation that involves each of the components of x separately. So we may be able to compute each of the components of x separately, and that can be a very significant step, right? If really you don't care about the whole x, you only want one component, here is a calculation that gives you that one component. Again, you notice here there's like k steps, I1, I2, ik, right, to do this b to the power k. So there are k steps, and then I sum for all possible steps k times hk, all right? And where is the important sampling, right? So what I'm going to do is I'm going to introduce, just to have a compact notation, these indices I1, I2, ik, I'm going to call them gamma k, and they're basically a sequence of indices from 1 to n, each of them, and there are k of those indices, that's why I put the subscript k, all right? So remember here it says sum from k0 to infinity, and then over all these possible indices I1, I2, ik minus 1, ik. So effectively, this is how the equation looks like. xi, if I call all of this thing, you know, if k is positive, I call this product. If k equal to 0, I call this hi. The solution xi is really the summation over all possible gamma k's, all possible indices, you can see here all possible indices of alpha I computed at gamma k, which means alpha I computed at a given sequence of k steps defined by I1, I2, ik. So, summary. We can write the component xi as the summation over all possible indices that involve these k steps, okay? And summation of the alpha i's defined for given indices gamma k, okay? And this coefficient alpha I is given explicitly by the derivation from what you see here. Can you give me a statistical interpretation of that equation? We may have seen something like that before. It's obviously discrete there, so you don't see anything expectations, but can you guess how we can make this to look a statistical equation? It says xi is the summation of the alpha i's for all possible indices of size k. Now forget Gibbs sampling. We haven't said anything about Gibbs sampling. I want to know, can we write this equation in a statistical way? Right, remember the definition of expectation. What do you do when you have expectation? Of a function under some distribution. You multiply the function of distribution and you take an integral over all possible values or summation over all possible values. So there's no integration here, but there's a summation. And I don't see a distribution, so is there any hidden distribution there? Uniform distribution over indices. So effectively, the problem is nothing else but the expectation of this coefficients alpha I gamma k over the uniform distribution over indices of length k. Okay? Now, and I write it like that because this distribution is not normalizable, so you cannot write exactly, like this. Okay, so this is the notation. So this is where important now sampling is going to come. Okay, rather than sampling from this uniform distribution over indices, we're going to create a new proposal distribution Q that will allow us to sample the indices. And effectively, we're going to approximate this. We're going to approximate this with basically the expectation under this distribution Q of alpha I divided by Q. These are the weights. You see that, right? It's like, you say multiply by Q, divide by Q. So the ratio of alpha I by Q is what you see here, and the rest is the expectation under this proposed distribution Q. Of course, this can only be useful if this proposed distribution Q it's something reasonable you can program in one line of the code. Okay? So again, xi is the component of the vector in ax equal b, any component, and it comes out that this is the expectation under any proposed distribution at this point. And this is a proposed distribution over indices of size k of this ratio of the weights alpha I divided by q for the given gamma k that defines this sequence. So what do we do with q? What do we select as q? And so we're going to take a random walk of k steps. So this is maybe for this course the first time that you see the concept of random walk, which is fundamental to many different problems in statistics and stochastic modeling. So we're going to take a random walk of k steps. And remember, the proposed distribution in principle has very little constraints, can be anything, right? So the random walk will do it for us. So this is how it's going to work. This proposal Q for a given sequence of gamma k will consist of a transition probability. Remember, I start from I. I always start from I, all right? And I end basically at k where I stop, okay? Because this is a chain of length k. So I take this proposal distribution for given gamma k as the transition probability from going from I to I1, a transition probability of going from I1 to I2, from Ik minus 1 to Ik, and then because I need to stop on this k steps only, I need to have a stopping probability Pik. And so the stopping probability would be 1 minus all of these transition probabilities. And you may say, and what do I select for transition probabilities? The answer is anything you want that is less than 1. All right, so you say I have index 1, 2, 3, 4. So from 1 I can go to 1, or I can go to 2, I can go to 3, I can go to 4. All right, so if you have k steps, there is a probability where you stop, right? And because you have a probability for stopping, you don't really need, when you implement this, to define k a priori. So you don't need to say what k is when you do this calculation, because you have a finite probability of stopping at any intermediate index. It's very important. You don't have to say do over 3 steps or 2 steps or 10 steps. No, because you assign a probability when you stop okay, the algorithm will stop at some k, and you keep taking these averages for the different k's that the algorithm will give you. So that's basically what you get is, you get the solution to be, so you get these samples, you know, and you compute this Monte Carlo estimate, and that's basically Xi. And most probably this is the first time that you see solving AX equal to B, one equation at a time. So you can actually get the component of a vector X without solving all the equations. All right, I don't know when, if you guys get excited with little things, but when I saw this, and this is, I don't know, it's 20, 30 years ago, you know, I got excited. I thought, wow. And the same authors actually have pushed these ideas to solving nonlinear equations, solving eigenvalue problems, and lots of other things, okay? So let me see if there is, so if, here is a sort of a little 2x2 example just to see the methodology. So this is A, the matrix B looks like that, and that's the analytical solution, so it's a trivial problem. And so we have basically two indices, right, 1 and 2, and then we're gonna have a stopping criteria. And so what I do, let me just go back. So what I do is I define the transition from index 1 to 1 to be 1/3, from 1 to 2 to be 1/3, and then 1/3 to stop, okay? And similarly from 2, 1/3, 1/3, 1/3. So basically if you take a sequence, actually let me show you there is a specific thing. If I take, for example, if I sample this indices 1, 2, 2, 1, and then I stop, then X1 will be B12, B22, B21, and then B1, divided by the transition probabilities from 1 to 2, which 1/3, from 2 to 2, which is 1/3, this 1/3, and then stopping 1/3, and you get -2. If you repeat this, all right, if you repeat this with different samples of this, what I call Markov chain here, and you start taking samples, you basically converge precisely to the exact solution of AX equal B, but one component at a time. So you may want to appreciate the fact that if you want to solve AX equal B, and X is very high dimensional, let's say it's 1,000,000 dimensional, and you only care about a few components of X, this calculation will save you an enormous amount of computing time, right? An enormous amount of computing time. So you will go, usually when you solve linear system of equations with matrices n by n, the cost is n to the cube, all right? The cost here is n times s, which is the average length of these chains that you build in, and capital N is the number of samples that you need to take from Monte Carlo convergence. So you go from n cubed to n times little s, little capital N. And these methods, literally, there is, you can, the reference is there. If you want, you can read it in comparison to everything you learn in school about very many different methods. These methods are extremely efficient, okay? Now, if you really care about all the components n, right? So then the cost becomes very similar to many other iterative methods for this linear system of equations. But if you only care about a few components, okay, the method basically beats every other method. If you're interested in using Monte Carlo methods for nonlinear equations, for eigenvalue problems, integral equations, it's all there, all right? Everything has been done. Okay. All right, so let's move from the importance sampling, and I'm going to try to tell you a little bit of things that you will need here and there for your homework. Okay, so basically, we would like to introduce incremental strategies for for doing type of Monte Carlo approximations. And incremental can mean that basically either iterative methods, all right, where we start taking some samples with the hope that eventually will be the correct samples from the target distribution, or can be sequential methods where maybe rather than taking samples from the two distributions, we'll create a sequence of distributions that at the end will give us samples from the target distribution. So these are ideas that go with Markov chain Monte Carlo, and also these methods sequential Monte Carlo. And I will cover sort of both approaches in the following weeks in details because they're very important for your research. So today I'm going to give you sort of a superficial understanding of what MCMC is, and I'm going to wait for sequential Monte Carlo maybe later in November to cover those topics. All right, so I need to do some jumping on slides now. All right, so let me, actually maybe not too much jumping on this yet. So let me, oh, what happened? Okay, so let me jump to Gibbs sampling, which is a particular class of this type of problem. So let's motivate it. Let's put all of these things up. So this is a standard example that is referred to in many books to motivate Gibbs sampling. So think that you have a nuclear plant that has multiple pumps. In this case, we have 10 of those. And you count the number of failures of these pumps at given times. So basically, you may already have seen this in other courses. When you want to model failures, basically you do this with a Poisson distribution. So here, if each pump fails with a parameter lambda I that defines this distribution, the Poisson distribution, effectively the number of failures is a Poisson distribution defined by lambda times the time. So this gives you the number of failures for, let's say, a given pump at time Ti. Okay? So the idea here is each pump fails following a Poisson distribution with its own parameter lambda. I'm going to define shortly what beta means. Okay, so let me, in case you forgot, by the way, this is how the Poisson distribution looks like with parameter theta, 1 over theta factorial, lambda to the power theta e to the minus lambda. These parameters lambda in the Poisson distribution, I'm going to introduce a hierarchical model for them, so I don't have to calibrate them in detail. So I'm going to take lambda I to follow a gamma distribution, and the parameter beta in the gamma distribution is going to be another gamma distribution with hyperparameters gamma and delta, just to make things interesting. Okay? So what I'm going to do is I am going to write I'm going to write this the posterior distribution. So what is the, so I have the product, all right, the product of overall pumps, and I have 10 of those. So what is this? This is really the likelihood term because it gives me the failures of the pumps, right? And each of them fails with parameter lambda I, and I have basically, I measure the number of failures at time Ti. So the parameter really in the Poisson process here is lambda I times Ti, okay? And so I measure the number of failures, okay? This is Pi at a given time Ti, so this is where the Poisson distribution comes. All right? Then we said that each of the lambda i's follows a gamma distribution. So I have to put this inside the product as well, right? So this is the product basically of the priors for each lambda I. That's a gamma distribution. And then beta is the same for all of them, and it's a gamma distribution with parameters gamma and delta. So you can actually think here, all right, because we do hierarchical modeling, this parameter beta is the parameter that links all the pumps together. So we're not, you know, if somehow we were putting an index I there, right, It's like modeling each of these independently, but the idea is, since beta links all of them together, we're using information from all the pumps to actually make inference. Because maybe one pump never fails, so how are you going to be able to do anything about that? Maybe another pump fails all the time, so you do this by having a parameter beta that is shared by all of them. Bottom line, we have a posterior, okay, given our data, that involves this parameter lambda and this noise parameter beta, okay, and this posterior looks like that, and it's of course unnormalized. I simplified here like this. Now, if you try to use any of the methods for sampling from this posterior, you're not going to make any of them to work. So if you try to use the accept-reject methods, they will not work. If you try some transformation methods, they will not work. This is too complicated. If you try important sampling, it's not going to work. So we need something else. And the something else, basically, is this genius idea that goes with the name of Gibbs sampling that says, you know what? Rather than sampling all of these parameters simultaneously, and we have actually, if you notice, we have 11 parameters because we have 11 lambdas and 1 beta. So it says rather than sampling all of them simultaneously, how about if you sample iteratively one at a time? Now, I'm going to tell you what the algorithm looks like, and you have used it already in your homework, right, when you did model selection. Obviously, when somebody tells you don't sample these 11 things simultaneously, sample one at a time, there's no guarantee that whatever way you do it, that actually sampling one at a time, it will actually give you samples from the distribution of 11 variables. Right? I mean, if you start saying sample lambda 1 this way, and then lambda 2, and then lambda 3, etc., there's no guarantee why at the end the samples you generate are really samples that are coming from this. Okay? But the Gibbs sampling actually will guarantee that. Okay? And so let's see how it works. So the idea here is to be able to apply the Gibbs sampling algorithm, you're going to have to compute the conditional distribution of each of the parameters given all the other parameters. Okay? You remember you did this in your homework. And the idea here is this conditional distribution, you can actually immediately see what they are, right? So if you look, for example, the conditional distribution of lambda 1, you can immediately see that lambda 1 follows with everything else fixed. It's a Poisson distribution. You see that? Lambda 1 some power, e to the minus lambda, etc. Similarly, lambda 2, etc. And if you look for beta, actually you can see that beta is also a gamma distribution. Beta comes here and on this exponential, so it's a gamma distribution. So bottom line is, you can, in this problem, you can immediately write down analytically that the conditional of lambda I, right, is a gamma distribution, and the same thing for beta is another gamma distribution that looks like that. So here is what the algorithm says. Start with some values of the parameters, sample lambda 1 from this, keeping all the other parameters constant, then sample lambda 2 from this, keeping all the other parameters constant, and etc., and then sample beta, and if you keep doing this, then at the end of the day, the samples you get will be samples that are actually coming from this joint posterior distribution. Okay? So let me see if we formally have the algorithm written somewhere. Well, here's the algorithm, okay? So for each I, from 1 to 10, you sample, given all the other parameters, you sample lambda 1, then lambda 2, lambda 3, etc. Okay? From this gamma distribution. But the way you notice here, the way this is written, there's no lambda 2 or lambda 3 or anything like that coming. So this looks so this is actually not only the conditional of lambda I, it's actually the marginal, there's no dependence on the other parameters the way that I see it. Okay? So that's easy. But when you look at the conditional of beta, that depends on lambda 1, lambda 10, and is this gamma distribution. So again, what has been accomplished, rather than sampling from a distribution that has dimension 11, you sample 11 times from distributions of dimension 1. Now, again, I'm going to say, but this iterative takes too much effort, etc. Well, yes, but sampling directly in 11 dimensions for this problem is not an option, right? You cannot do it, okay? So this is very powerful. All right, so effectively, what have we done this? So let me try to, I'm going to tell you infinitesimal little things so we can move on in the lecture today. So what have we literally done here, right? Effectively, we are going to create a chain of samples of the parameters. We start with some values and then we keep moving. We update basically the samples. And this chain that we create is called a Markov chain, okay? And the way we actually create this Markov chain is by defining what's called a transition kernel. So, given the values, let's say, of the variable x at state n-1, somehow we have a rule that tells us what's the probability of xn belonging to some region or just taking a given value, and we call this the transition kernel. All right, so basically in the Gibbs sampling, there is a transition kernel, all right, but somehow given the previous state of the parameters lambda and beta, it tells us what to do next. And it's hidden, you don't see it. I gave you the rule. I said we sample from the conditional, so I'm going to try to generalize this to Markov chains and give you explicitly what is actually the transition kernel that allows me to go from xn minus 1 to xn in the context of Gibbs sampling. Even though the way we generate samples of the parameters lambda, right, we correlate them because you say sample lambda 1 given all the other parameters, all right, so it depends on all other parameters. We cannot really guarantee that somehow we can use this estimate as the Monte Carlo approximation that we have seen before, because in Monte Carlo approximation, the samples are independent of each other. There is no guarantee, basically, nothing here. The samples are correlated. Well, yes, but as n goes to infinity, actually, this is true, and actually, indeed, the samples are samples from the actual distribution pair, even though they're correlated. Okay? So, basically, what we learned from Monte Carlo, asymptotically, the same thing, it is true with certain constraints that we will, if I have time, I will at least casually mention, and we will see them in detail in follow-up lectures. So this requires a number of constraints in the way that this transition kernel is defined, okay? But under some weak conditions, it is possible that indeed this will be the case. So just a simple example, okay? Of a Markov chain here is an autoregressive model. So basically we pose a rule on how to go from xn-1 to xn. The noise we use is a Gaussian. Really, this is a random walk, okay? This is what it is, right? The probability of xn given xn-1 is a Gaussian, okay? So I can tell you that if you do this problem theoretically, this chain that you see there converges to this exact Gaussian. All right? So we actually know what the right answer is going to be. But if you want, what you can do is write a little program. Start from any distribution of xn-1. Take samples of this, let's say at x0 to be samples from a uniform distribution. And then following this rule, keep updating xn and keep getting new samples of x1, x2, x3, x1000. You will find out at the end of the day that those samples are actually samples from this exact Gaussian, which is the limiting distribution of this autoregressive model. And I'm going to show you a picture that demonstrates, all right? So, for example, if you, this is, your target distribution is a Gaussian. If you take samples that they are uniformly distributed, and then you start moving them with this random walk, after about 100 steps, you basically, all your samples are coming from the Gaussian. Okay? So, I mean, this of course is a simple example, but you need sort of to appreciate that under some conditions, we would be able, with good luck, basically to converge to the actual target distribution, and then we can guarantee, if we do Monte Carlo approximations, that actually would be valid. All right. So actually, so basically in summary, right, like we did in Gibbs sampling, where we generated samples of these lambda parameters and the beta, so we somehow, if we sequentially, have some rule to generate the samples asymptotically when n is large, all right, we will be able to approximate expectations under the true distribution pi of x, but by actually taking the samples on the chain and doing the regular Monte Carlo estimation. I mean, if you think this sounds not being right, because when you generate samples, sample xn depends on the values at step n minus 1. So all of these are correlated, but if you all take them together, all right, and somehow do this type of calculation, then this is a good approximation of the exact expectation the way we have seen with Monte Carlo. Not only that, you can actually show that asymptotically the rate of convergence under some constraints is actually 1 over square root of n, the same thing as vanilla Monte Carlo type of calculations. All right. So there's a number of constraints that need to be satisfied when you generate these chains, and so I'm going to try to give you progressively at least the buzzwords for them. So the first one is that the desired distribution P from where you want to sample needs to be the invariant distribution of the transition kernel P. So I want you to look at this equation and tell me if you physically sort of understand it. I remind you that this transition kernel P of x and y is a rule that tells you if you are at x, you can move to y. So we want with that transition kernel to eventually create samples from the true distribution pi of x. So it says for this to be happening, right, the distribution pi needs to be an invariant distribution of the Markov chain, which implies this equation. So I want you to look at it and tell me if you understand it physically. What does it say? I mean, at the end of the day, right, if pi of x, if all the samples are going to be coming from the true distribution, so when you're at x and you move to y, for all possible values of x, what should you get? You should get P of y. Okay? So, so in many ways, this equation is sort of an obvious argument here, all right? If you're at x and you transition to y, all right, for all possible values of x, you should get pi of y, okay? So, so this is one of the constraints that are going to be required for us to be able to approximate expectations with classical Monte Carlo estimates, and even more importantly, to claim that asymptotically xn are samples coming from the true target distribution pi. So there is two more, okay, let me go back. I don't know if the slides are on these things, but because most probably we will not have time to discuss all of this. So there are two more very important requirements to make this to work. All right, so we mentioned that pi has to be, so the first requirement that we had, it was this equation, but there is an additional requirement, two of those, that have a lot of substance there, and one of them says the chain has to be irreducible. And this is not actually something to take in a very light manner when you develop algorithms. So what does irreducible means? Does anybody know? So I have this chain and we want it to be irreducible. Maybe the English word is not the best for what it's intended for, but what does irreducible means? So think, right, that this is, let's say, the space, the 3D space, is all potential values of this variable x, okay? So you start from here, and then you have a rule, you move there, you move there, you move there, etc. What will be a requirement that you will expect this transition kernel to satisfy to be able to actually sample the whole of this rule? I mean, would you be happy if I keep moving here around and never come there? So how should we state that requirement? With words, basically. We need to be sure that if we start at any location, there is a non-zero probability from that location to be anywhere in the domain of the distribution. I mean, if I cannot reach there, means I will never see that sample, I will never be able to generate. So I will never be able to say that I actually sample from the true distribution. I need to have a finite probability that I can go from any location to anywhere else. So this is, in common sense, you should not allow to be stuck in one domain, okay? Because if you get stuck, basically you'll be exploring locally, you'll never be able to go somewhere else, okay? So this goes with the name irreducibility, finite probability to go from any location to any other location, and then your chain needs to be aperiodic, okay? Effectively, when you explore the space, you should explore the space not in a periodic fashion. So if let's say if I am going to visit you, right, and I'm from here and I move around, etc., I should not visit you every 5 steps. I should visit you maybe now in 5 steps, then next 35 steps, 1,000 steps, million steps, but not every 5 steps. This is what is called aperiodicity. So when the previous equation, irreducibility and aperiodicity are satisfied, you can actually prove mathematically that the chain will actually give you samples that are coming from the true target distribution. I don't want you to take sort of these statements light, right? Because in many problems that you play with complicated data, somehow you're going to have to use some perturbation of existing algorithms because you need to fine-tune things. And if you fine-tune, if you're going to do random walk, what steps do you take on the random walk? Well, I can take very small steps, and you know what? I will never be able to explore the whole space. All right, so let's say if I'm here and I can only move, a millimeter, I will never be there. All right, I mean, never in my lifetime, basically, okay, in a finite time. So we basically need to be sure that the selection of parameters and transition kernels we do, they satisfy these conditions. All right, so let me demonstrate this transition kernel back to Gibbs sampling. And I'm going to use, that's the easiest example actually to do it. I'm going to assume that the target distribution has 2 random variables. It's 2-dimensional, θ1 and θ2. Okay? And so this is how we start with some values of θ0. Okay? And we sample at step I. We sample θ1 from the condition of θ1 given θ2. But you notice, what do I use for θ2? I use the values of the previous iteration. And then I sample θ2. And what do I use for θ1? The value that I just sampled. Okay? So, so I'm going to ask you shortly, if this is on the next slide, to tell me what's the transition kernel for this problem. Yeah, well, let me remove it. You guys tell me. So I want you to look at this and tell me what is the transition kernel of going from θ1, θ2 to, let's say, θ1 curve, θ2 curve. What is the transition kernel? What is the rule based on this algorithm that tells me how to go from theta 1, theta 2 to theta 1 prime, theta 2 prime. What's the rule? So what's the transition kernel that tells me how to move from theta 1, theta 2 to theta 1 prime, theta 2 prime based on this algorithm? So you said multiply of those two, right? Some sort of. So let's say we need the rule for going from theta 1, theta 2 to theta curl 1, theta 2 curl 2. So would you agree? When I sample theta 1 with this conditional, I keep theta 2 to its previous value, theta 2. And then without theta 1, I use the condition of theta 2 given theta 1 to sample this curl theta 2. So the transition kernel for Gibbs sampling is this. All right? Remember, and we will see this when we do, in other algorithms here, the transition kernel is not the same as the importance distribution, right? The transition kernel gives us the probability rule of going from this sample to the updated samples on the next step. And in the Gibbs sampling algorithm is really the product of these conditionals, but you have to be careful in the notation. This is the new sample given the old one, and this is the new sample of theta 2 given the sample of theta 1 that we just sampled from the first conditional. Make sense? Okay? Now you may ask, does this satisfy actually this, is pi an invariant distribution of this transition kernel p of x and y? By the way, another word that is used, basically it's most probably more common for this equation, this is called the Dittel balanced equation. Okay? People actually who play with Monte Carlo methods in biology, in chemistry, they will, this is the Dittel balanced equation. So the question here is, if we're going to really have any hope for this algorithm, the Gibbs sampling, to work, the first thing we need to demonstrate is that this equation is satisfied. Is it satisfied? Well, it's just a little bit of algebra, and it's nothing actually to it, and I think you really need to do the algebra to appreciate that you understand what the algorithm is. So what I have here is, I have p of x, so that's p at the original samples, and then I have the transition kernel from theta 1, theta 2 to theta 1, theta 2 curly, d theta 1, d theta 2, right? And so let's see what happens here. I put things in blue, so they're easy for me to even make sense out of it. I write the transition kernel with the definition we have there. That's what it is. So I put this in blue. There is theta 1 only coming on this term. So when you integrate this in theta 1, what do you get? You get the marginal of theta 2. All right? So you have the margin of theta 2. So if I mix those two together, I get the joint of curly theta 1 comma theta 2 times this condition of theta 2 given theta 1 d theta 2. And when you integrate this in theta 2, what do you get? The marginal of theta 1. And those two together, that gives you the joint of theta 1, theta 2 curly. So actually, you can see the Dittel balanced equation satisfied. Okay? You can actually prove the rest of the conditions as well. So I am going to actually, we don't need to discuss this. So certainly for the Gibbs sampling, you can actually, at the end of the day, when you take the samples, you can guarantee actually that they're coming from the target distribution, okay? So certainly you can do your Monte Carlo approximations, and if you really want stronger statements to actually say that theta 1, theta 2 are samples from pi, you can do that as well. So this is a much stronger requirement. Okay, so we mentioned those with words, we don't really need them. Okay, so I'm going to give you two versions of the Gibbs sampling algorithm, then we will move on. All right, so here is the, I have theta is a vector with p dimensions, p is greater than 2, okay? So a little bit of a notation, because we are going to update one variable at a time, so let's call this variable k. When you see this theta minus k is the vector of all the variables theta except k. All right, that's a standard notation. So when you see theta minus k is all the variables except k. So what you do is you are sampling from the conditions of theta k given all the other variables. And you have to be careful what all the other variables, what values are they going to take, okay? And notice here, the variables from 1 to k minus 1 have an index I because I already have updated them from the previous step. And all the other variables k plus 1 to p have not been updated, so we'll be referring to iteration I minus 1. Okay? So again, it's minus k, but also pay attention to the indices on the top. All right. So this algorithm goes basically with the name systematic Gibbs sampling, because you sample in sequence basically theta 1, theta 2, theta I, etc. Okay. There is actually a better algorithm. Can you think of an algorithm that may be sort of more efficient than doing things in sequence? Give me your own algorithm. So here we have a vector of p values, right? And we sample in sequence theta 1, then theta 2, then theta p. So give me something else that may be even better. And actually not even better, the algorithm would even be one line. Not like, many lines, just one line. Or two lines. So rather than sampling in sequence, what else can you do? How about if you say, look, from all the variables 1 to p, let me randomly select the one to update, and keep doing this. So how are you going to select which variable to update randomly? What would be the rule? You're going to be sampling from where? From what distribution to figure out what variable you update, if it's going to be 1, 2, or p. You know what? I have hearing problems. From what distribution? The uniform distribution. All right. So that's the algorithm. All right. So this is called the random scan algorithm. So basically, we will sample an index k from the uniform distribution over the indices 1 to pi, and we will set all the other variables to whatever values they have. Okay, as before, and then we just update the theta k, and then that's it, done. So basically, you don't go in sequence. You say start updating randomly whatever index you select through this. Okay, so that's why this algorithm is called a random scan algorithm, and you can actually do even fancier things, right? There's a lot of versions of this. Rather than sampling one variable at a time, sometimes it may be to your advantage to sample blocks of variables together. So rather than sort of, in this case, updating a variable k, you may want to update several variables simultaneously, because maybe those variables are so highly correlated that it makes a sense to actually put them together. And so the algorithm in that case, it's actually called block Gibbs algorithm, because you use conditionals, but conditionals over blocks of variables. Okay? The nice things, right, if it will take you literally 1 minute to find the best algorithm in any language you want anywhere, because people have worked these things out for you. But you need to know what they are, so when you write a paper and you say, I'm using Gibbs sampling, you can actually add a line and say what Gibbs sampling, you're using, etc. Okay, so things they're not magic. They have some, they come from somewhere. Okay, so so what I have here is I have a way to actually take samples from bivariate distribution with a correlation coefficient rho. So in this case, I give you exactly the conditionals are also Gaussian, very nice distributions. Okay, x1 given x2 and x2 given x1, and actually let me actually go fast through the things. So if you look at the histogram of x1 that you generate, it actually it's a Gaussian, and this is the x1 x2 plot that somehow tells you that you are not stuck anywhere. You notice things are more or less all over the space, okay? But then look what happens. If you take the correlation coefficient to be 0.999, all right, and you look at the sample of x1 and x2, this is how the change of events go. So it's like, you get something, then it moves there, then, So do you explore, are you concerned about this? Yes, of course you should be concerned. It doesn't seem that you explore the space correctly, and you have troubles because the histogram that you get, it actually doesn't match the Gaussian. Okay, so so in this case you need to, you have an issue basically. There's a lot of implementations of this with nice animations. So if you want to implement the Gibbs sampling actually for the bivariate distribution, literally, if you want to do it sort of in a two lines code, this is given x2 how you update x1, where this is a sample from a standard normal, and here is updating x2 given x1, a sample from standard normal. These are the coefficients, the covariance metrics, and and you can follow basically how accurately you represent the distribution. You can do this for a Gaussian mixture, right? So if you have two modes, you need to be sure that somehow when you do Gibbs sampling or any other algorithm, you're not basically trapped in one of the modes. So you can see here, it seems to work. You generate samples from both modes. I think in one of the presentations, you can imagine actually on this problem, right? If you do, let's say, random walk, and you start with some samples, maybe if the random walk has very small steps, very small variance, you will never escape from the mode that you started, so you'll never be able to jump from one mode to another, okay? So you need to be able to jump from one mode to another, otherwise you will not get the right answers. I don't think I will have time to tell you about Metropolis Hastings, so let me give you an example, and I think that example comes from the book of Bayesian Core, and it's a cute example, okay? So, something that basically the Gibbs sampling is not obvious that it's relevant, okay? So, you have a likelihood model, and you collect two samples, x1 and x2 from the likelihood model, and the likelihood is basically a Cauchy distribution. Okay, so remember the Cauchy distribution is 1 over pi times this term inside parentheses. So you have two samples, IID. So the likelihood looks like that, and you want to compute the mean. You want to inference, Bayesian inference on the mean of this Cauchy distribution. So you're going to put a prior of this. So you put a prior that's Gaussian, and then the posterior looks like this. So my question to you is, can you apply Gibbs sampling to this problem and tell me, does it even make sense to talk about Gibbs sampling about estimating mu in this problem? How many parameters have in this problem? Only one. So what Gibbs sampling am I talking? There's no Gibbs sampling here. Gibbs sampling, you have to have more than one parameters, right? And compute the conditionals and all of these things. So if you try to play with other methods, right? And this can be sort of a very painful homework, try to do various other methods, you are not going to succeed. Here is a trick, how we're going to make Gibbs sampling to actually work on this problem, even though we only have one variable. All right? So I give you the trick. You can actually show that 1 over each of these terms, 1 over 1 plus xi minus mu squared, it's actually the integral of e to the minus omega I times that from 0 to infinity. Help me now. How can I do Gibbs sampling, or why it's relevant? Why is this equation relevant?
Now we have like two parameters, omega and mu.
So now what we can do is we can actually work in a space of 3 parameters, mu, omega 1 and omega 2, okay, and do Gibbs sampling in that space. And actually once we're done, the only thing we need to do is keep only the samples in mu, all right, because those are the only samples we care. This, by the way, doesn't look like a very weird approach. In lots of problems, it may be easier to work in a bigger space, all right, even though you don't care about many variables in that space, but somehow, let's say here, when it comes to sampling, you can actually use Gibbs sampling in the enhanced space, okay, and then only maintain the samples in mu, and that will give you basically samples from the actual posterior distribution. So how the whole thing looks like? So you work on this enhanced space, okay? And you can, if I ask you what is the conditional of mu given these coefficients w, or if I ask you what's the condition of w's given mu, the answers are actually exact. So the condition of mu given the w's is a Gaussian, and the conditional, where is it? The conditional of omega given the mu's is an exponential distribution. You remember when we discussed about the transformation methods, I told you how to sample from the exponential distribution. So this is Gaussian. So you do Gibbs sampling of this problem, and when you do Gibbs sampling, you can actually generate samples from a distribution that's sort of a product of Cauchy and Gaussian terms, and it looks very well. Okay. So again, we do this. We get rid, we don't care about the samples. Remember, when you have a Monte Carlo approximation with many different variables and you want to marginalize, you only keep the particles for the variable of interest. The rest are integrated out. So here you computed the samples on the W's, but you marginalize them out and you don't care about them, and the only thing you do is you keep the mu's and you do a histogram, and that's the actual distribution that's coming out. I don't, I mean, I already have done this, right? But I remind you, you remember this problem? This was what you worked on the homework, where we use, we had basically a regression model, and we wanted to figure out how to select the input variables that are relevant to explain the model. So we transformed a regression problem to a model selection, and we introduced basically, this syntax is gamma k that define the variables that they are activated. And somehow the calculation was not very complicated, but you use this, I want to believe you use this in your homework correctly. You computed a conditional of gamma k given all the other variables, and somehow together with conditionals of the coefficients beta and the variance sigma in the model, you were able to effectively do Gibbs sampling, and at the end somehow you were able to evaluate everything in the problem, right? Even the marginal likelihood. And so you had an algorithm that was looking like this. Right? So you were basically doing a selection of models, and then for each model you were updating the parameters and you keep iterating on this. And this was sort of a weird form of doing Gibbs sampling because you were mixing continuous and discrete variables in doing this type of thing. Gibbs sampling is extremely powerful, okay? It doesn't work in many important problems, but Gibbs sampling may be a small part of other very complicated algorithms. It's essential. You need to know it, okay? And the next algorithm that you need to know is Metropolis Hastings type of algorithms, and we will discuss those later this week, okay? All right, so I'll see you. I'm not going to tell you I'll see you. I will see you. We will have a lecture on Thursday. That's as much as I can say. Okay, so I'll see you. Thank you.
Do you have that?
Tell me to, oh, yes. You saved me.
No problem. Thanks.